Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. And I'm glad that you have taken the time to join us today as we look at our topic of 4 methods to reduce scrap and rework in your manufacturing process. Now, scrap does happen, and as we get through our presentation today, if you have any questions, feel free to pop those into the chat, and we'll look at those after the demo portion of today's presentation. But scrap does happen, unfortunately, in the world of manufacturing. And there are a couple different categories of scrap that happens. And first is going to be rejected in the raw material form. So that part of the items or material are scrapped at the outset. And then we have scrap that has been partially processed but did not meet specifications or maybe got damaged in the process of movement through the facility, or it could be a number of different reasons why that particular item may not necessarily have been processed correctly. And that would lead us to the final category, which would be the failure to meet the specifications at the end of the manufacturing process. So all of these array of items are scrap, and they all include extra material costs, extra labor costs. So anything that we can do within the process of the manufacturing, especially as it deals with fastening and fastening errors, are going to help to reduce those scrap rates for you and your process. And that's going to lead us into what we're kind of talking about today, and with our advances in the manufacturing tooling and in the manufacturing process. So there are ways that new tooling, especially around the world of smart tools or DC controlled tools, these help in executing those specific processes very, very nicely. The ability for the tools to communicate with line control devices, with the ability to control what happens during the rundown with the tool itself, has brought us to a place where we can have a lot of control about what's happening. And this gives us a great deal of flexible automation systems to be used, whether that is through an MES system and communication to that, through a PLC and other type of line control devices that allow us to be able to have a lot more control and a lot more communication about what is happening with that process. And the ability for us to monitor that during that particular build or particular operator using the tools help us again with all of that within our data acquisition systems, and the ability then to look at what's happening with that, and on top of that, having extra capabilities to error proof what happens during the actual assembly. And we'll talk a lot about error proofing today, which allows us, it's kind of the cornerstone of being able to reduce those scrap rates. So causes for defects that we look at typically, the biggest contributor to defects is going to be the operator themselves. Sometimes the operators aren't paying attention to what they're doing. They can over tighten things, under tighten things. They can skip fasteners, or they may let go of the trigger too soon in a fastening operation and leave fasteners lifted. So we have zero clamp force on a particular fastener, which may necessarily need to be there to keep our parts together. So the operator plays a real big part in the operation, of course. And so anything that we can do to help minimize their influence can go a long way in that process as well. And so Some of the common tightening common tightening failures that we typically see are going to be those, again, fasteners that may be under torqued, not providing enough clamp load that we need for the parts to remain intact. Any type of vibration or shock can cause that fastener to fail even more. The opposite of that would be if we're over torquing a particular fastener. And this can certainly bring our fastener to its yield point, meaning that it's stretched extremely far. And if there's any type of vibration or shock that can cause that fastener to break and fail, and then we have, again, lost our clamp force with that. Again, operators not paying attention to what they're doing. Again, not hitting specific fasteners that they're supposed to in a correct pattern or in other types of processes. So again, these are some of the common tightening failures that we see within the process out there. So that's going to lead us to our poll question for today. So if you want to go ahead and launch that poll, and so we're just looking at to kind of estimate what your current monthly production scrap rate might be. And that can go ahead and be less than 1%, 1 to 2%, 3 to 5, or over 5. So I'll give you a moment here to go ahead and answer that poll, and then we'll be right back with the rest of the presentation. All right. Thanks very much for participating in that. And it looks like the majority answer there was 1 to 2%, followed by less than 1, and then 3 to 5, and then 5% more. So again, thanks very much for participating in that. And hopefully some of the information that you will get today can help to reduce those factors for you in the future. So what are the 4 methods for reducing scrap? So let's first talk about error proofing and the error proofing process. So this is a widely used topic coming from the Japanese poke-yoke, which basically in essence means that we're giving the operator the opportunity not to make a mistake. So, we see error proofing in our everyday lives. Things like if you're going to start your car, if you have an electronic push button to start, your foot must be on the brake to start the car. This helps to make sure that you don't accidentally roll off or into traffic or anything like that. But again, a safety measure to error proof when you start your vehicle. It also could be if you're using a plug and electrical outlet. You're going to have one side of that one side of that plug is going to be larger than the other side to make sure that the plug is going in the right way. And things like elevator doors that have safety mechanisms built into them so they don't accidentally crush somebody, and things like that. So we do see the error proofing process throughout our everyday life, and if we can take some of those error proofing things and we can apply them to fastening, then this is going to help us again accomplish our goal and reduce our scrap rates. And so when we're looking at fastening, and through that we can go ahead and we can ensure that we're getting the correct torque that we need from our correct part location with our error proofing process, where we can detect if there is a fastening error within that particular rundown. Then we can go ahead and we can address it right at that moment and make sure that that fastener is done correctly. And again, through the demo process that we'll go through, we can look at things on how we can accomplish that as it relates directly to the fastening process, making sure that all of the fasteners get torqued, that they get torqued correctly and in the correct process. which leads us to our second method here, which is our process control. And this is creating a program assembly sequence of our fasteners. And again, that sequence can be different preset values, different torques, and possibly different bits that can be used within the process itself. And we can control all of that through the use of our advanced smart tools to help with the process. Another thing that we can do is make sure that each fastener has a specific tolerance that can be programmed for through the use of a specific preset. So for example, you could have a fastener that has all of the same recommendations for the torque, could be the same size, but the only thing that's different is the length. And if you put that shorter fastener in where it's supposed to be the longer fastener, you could have some issues. So we can control some of those tolerances around a specific fastener. Even though the torque values may be the same, we can detect to make sure that the correct fastener is being used in the correct location. And again, we can have multiple tasks, fastening tasks, as I just mentioned, within the process control itself. And if we do have a scenario where you do have multiple tools at a specific workstation, that you may have 3 or 4 different torques, and you may want to consolidate those particular items into one tool. We can do that with our smart tool as well to help consolidate that particular functionality of that cell. Next is going to be the use of a transducerized tool within the process. And what this means is that we have a sensor that is built inside of the tool, and it's giving us the real-time monitoring feedback of the torque that's happening for that. And again, that is really vital in making sure that we're hitting our correct torque values, that we are within our specific torque tolerances that we may need. And all of those can be programmed for a specific preset, as I mentioned. Now that's going to lead us to our third method, and that is going to be the automatic data collection and recording all of the information that happens from a particular rundown on a particular tool. And as we get more and more into the use of MES systems within the actual process, where we're taking data from a particular fastener and we're importing that for a record's sake within the actual process or the actual work instructions. Data collection is a valuable part of that. And with the use of different protocols, our digital IOs, and our connectability of our tools, this does give us that ability to export those items in real time. And it does give us the ability to make really good data driven decisions. So we can look at how a tool performs over time. We can also look at how a particular joint may be faring. We can also look at how different shifts may be using the tools, or how they are processing through the actual assembly. And then you can also look at different operators and things like that. So as long as we have data to look at, we can parse it and look at it however we might see fit to improve our process. But it does give us that ability to get much better at our process. And again, then we have better abilities to have a better response time to issues that we may see within the actual process or the assembly or a specific joint. And then we have the ability to optimize again and improve that productivity through the use of that. Now, the last item that we have here is fastening automation. And so what this means is that we're taking some of the processes that the operator may may have to do manually, and we're basically converting that into an automated process. And this could be things like changing a preset on the tool. It could be making sure that they're using the right bit for a particular fastener. All of these things that if there are potentials for error can add up over time and again increase the scrap rates based off of insufficient fastening for the operator and they're using. And so with the use of our digital I/O interface, we can communicate again with proximity sensors, with line control devices, with PLCs, and other items that we can use to help optimize and make sure that the fastening automation process is working correctly. And so these are the 4 items. Again, we can error-proof the assembly process. We have process controls in place. We have the ability to collect and analyze our data. And then we also have fastening automations. And so this is the setup that we're going to use today for our demo. We have our MDC DC control tool that we'll be using. And then we also have our DPC touch control torque arm. And this particular setup allows us to be able to accomplish a lot of different things. Here is our thread block that we'll be using as our part. We have these 3 fasteners here, and they will represent the items that we need to go ahead and torque. Then we have our DPC touch here, and then our MDC TD control tool, and our driver here in our torque arm. And so what we have the ability to do here is we can make sure that the operator is using the tool in the correct location and that the correct preset is being used for that particular operation. If there are changes, again, as I mentioned, in the profile that may be used or the preset that may need to be used, we can control all of that here through the DPC touch. This is going to allow us to have up to 256 different fastening jobs. Each of those jobs can have up to 99 steps, and each step can have up to 99 fastenings. But there is quite a bit of power that we have available in the DPC touch unit. It works in conjunction with the torque arm. The torque arm does have 2 angle encoders that allow us to monitor where the tool is in space, and then it will coincide to the fastener that we're using, and giving us the ability to make sure that there is power only to the fastener that we need to be used for that particular assembly. And so right now you can see on our controller here that the tool is locked. There's no power to the tool, so if I try to use the tool, we have no ability to do so. So let's go ahead and look at our process here, and this will allow us to show you and demonstrate some of the features that we can use in the way to reduce our scrap rates here. And so we have a picture of our part here, and this can be basically of anything that you have that you're working with. I obviously don't have a V8 engine here on my desk, but nevertheless, this can give you a representation of what you need to, or what you can use for your images. And so as I move the tool into the correct location, you can see that our controller becomes enabled, and we are able to use that in the correct location. If I move outside of that location, you can see the tool then becomes locked again. The screen on the DPC touch changes its from its state, so from red to yellow, and then finally to green, that we are in the right location. So if I try to go to the fastener next door, again, the tool becomes locked. So we can only use this preset here, preset 1. Now, what we're going to kind of emulate is a multi-pass type of scenario. We're going to use the same 3 fasteners, but we'll use them in 2 different steps. This first rundown is going to be simply an angle step, where we're going to rotate that fastener 800 degrees of rotation. And this is, again, kind of mimicking a flange type application, or some type of seating application where we need to try to bring the parts together in an even fashion. And that's one of the different fastening strategies that we have available on the control unit. We can either run to a specific torque value, or we can run to a specific angle that we have here. And so if we go ahead and run this, we'll go ahead and get that. So we got a good result from the controller that allowed us to communicate to the DPC Touch that we got a good rundown, and we've now indexed to our next location. You can see that we ran our 800 degrees of rotation, and we'll go ahead and move to the next step. Again, we're using preset 1. We got a good result. It is now indexed to the third fastening location. And now we have moved back to our first position on our fastener. And now this one is going to be different. Now we've changed our preset to preset 2. We're going to be running to 40 Newton centimeters. And this is our newer transducerized low torque version. And we can go from a very low 7-inch ounces all the way up to 97-inch ounces. 1 inch to 70. Yeah. So for this fastener, it's going to be preset 2. For this fastener, it'll be preset 3, and this fastener will be preset 4. And we are moving up in 5 Newton centimeters increments as we go. And then on the last one, we do have, I'll show you one of the error proofing functions that is. So let's go ahead and run this down. All right, we got a good rundown here. Now we move to our next location, preset 3. We have changed our preset, and we're now at a target of 45 Newton centimeters. Now we've got that. We moved to our third fastening, and what I did put in here is, let's see. I put in a error proofing step. So if we are dealing with sometimes fasteners that can be stripped, if they go too far in the assembly, we can put a maximum amount of turn per step or per preset that will go ahead and let us know that we have gone too far, and it's possible that that fastener may have stripped. So if we run this down, so we did, we got our angle over the limit, and you can see here that it changed our values, or excuse me, it didn't count that value. We can go back out. We're still on this third fastener, and it rejected that fastening. So we did not get a good signal back. Obviously, we got the alarm, and that triggered the process. Now, we can tell the DPC Touch that we can have up to 9 reattempts, or you can set that value at whatever you would like, from 2 reattempts to 5, whatever you want within your process. But we can go ahead and set that, and we can run it down, and then the unit will go ahead and either start back up, or we can set it to a different job. Or we can, again, have this connected to a barcode scanner. We could scan a part So if there is kind of a high mix, low volume type of scenario where you've got multiple different setups that may use different presets, we can do that as well with these control units. But again, we do have that ability to error-proof the assembly through the use of torque and angle monitoring. We have the ability to make sure that we're using the process controls correctly by setting up the assembly. We have the data acquisition portion that we can use from the controller to stream out either through our RS-232 port or our Ethernet port on here. And then finally we have that whole excuse me. Okay. Sorry about that. With that, that'll go ahead and conclude our demo for today. I need to grab a drink of water, and that's going to lead us to our questions. And so, Chris, do we have any questions?
Morning, Dave. One of the questions we have is, what is the difference between a transducerized and a non-transducerized tool?
So the basic difference is that a DC tool can come in two different types of tooling. The transducerized tool has a sensor that is built into it that is allowing it to monitor the torque value from that tool. And then that tool is basically being controlled by that sensor and giving us that ability to read the actual torque output. The other form of DC tool is going to be a current control. And so this correlates a torque value to amount of current draw that happens within the tool. Now, both tools are very accurate, but the transducerized tool does give you that ability to get the actual torque value instead of a converted torque value that you would get with a DC control tool.
Another question we have is there what would you recommend for a fastening strategy when it involves like Loctite as a patch applied to the fastener?
So Loctite can introduce some variables in the actual clamp force that's being delivered. And if the testing that was done for the actual torque that's being applied was done with the Loctite, that's going to give you a much better result than if you tried to use the Loctite afterwards for that torque specification. Because if it is going to be put on in its liquid form, then you're going to be changing the coefficient of friction during the actual rundown, and that can create more tension on the fastener, meaning that because the resistance of the fastener when it gets to the bearing surfaces is going to be less, we're stretching that fastener more, and that could be certainly an issue. Now, if you have a patch that you're dealing with and you need to cut the threads, and in some scenarios there may be that ability where the cutting is actually higher than the seating torque. We do have modes available within our control tools that allow us to disregard that high point during the cutting portion. And then after the cutting, when the fastener drops back down beneath the seating torque, it will then look for the seating torque. There are a couple other ways that you can deal with that as well. We do have a multi-sequence process that allows us to combine different presets together in one operation. So if you do have a cutting type of scenario where you need to run maybe an angle preset and then followed by a fastening preset, we can use those in conjunction in one type of operation. And so that can be accomplished that way. I hope that answered the question.
All right, Dave. Another question we had is, how many workflows or fastening sequences you said can be stored with the system?
So on the DPC Touch, you can have up to 256 different programs. Those programs can contain 99 different steps, and those steps can have up to 99 fastening points. So it is quite a large array of different profiles that you can have on the DPC Touch. On our standard DC control tools, they allow us to have 15 presets and our two multi-sequence presets that we can use. We can also have the system connected to a PLC, and that PLC could read and write to specific values and parameters within the DC control tool. So in that case, we can have basically an unlimited amount of presets where it can, based on the job that is coming in, it can write all of the presets that it needs for that, the parameters around it, and there's that communication. The standard DC tools will be expanding here soon to allow us to have up to 31 presets, but that is still in the future. But there are different ways that we can handle different amounts of items that are needed.
All right, thanks, Dave. And I think that was the last of our questions.
All right. Thanks so much for joining us today. I hope you found some useful information and that you can implement that and use it in your processes. Again, thanks so much, and we'll see you next time. Have a great day.